waves reach a point in space at the same time. The resultant displacement of the particle is given by the principle of superposition. According to this principle, the resultant displacement, y, is the vector sum of the displacements y1 and y2 caused by two waves. For coherent sources, the waves generated by them will have the same amplitude, same frequency, and the phase difference between them is constant with respect to time. The waves from coherent sources can interfere constructively or destructively. If they interfere constructively at a point, the individual displacements are numerically added to give the resultant displacement at that point. When they interfere destructively at any point, the individual displacements cancel each other and the resultant displacement at that point is the minimum. You have already learned that for constructive interference, the path difference must be equal to n lambda, where lambda is the wavelength of light used and n is an integer. In terms of the phase difference, phi, the condition for the constructive interference is given by phi is equal to 0 or plus or minus 2 pi or plus or minus 4 pi and so on. For destructive interference, either the path difference is equal to n plus half into lambda or the phase difference, phi, is equal to plus or minus pi, or plus or minus 3 pi, and so on. If light has wave nature, it must exhibit the phenomenon of interference. When Huygens proposed the wave theory of light in 1678, there was no experimental proof for the interference of light. Subsequently, in 1801, Thomas Young demonstrated experimentally that light exhibits the phenomenon of interference. Let's study about Young's double-slit experiment. Take an opaque screen with a small pinhole S and place a monochromatic light source to the left of the screen. Now, the pinhole S acts as a point source of light and propagates spherical light waves to the right of the screen in all directions. Place another opaque screen with two very closely separated pinholes, S1 and S2, to the right of the first screen. When S1 and S2 are illuminated by the incident light from S, they behave like two point sources of light and emit spherical waves to the right of the screen. In fact, S1 and S2 behave like virtual coherent sources of light. These spherical waves from S1 and S2 can be made to interfere on the screen GG' placed in their path. They form a series of bright and dark bands called interference fringes on the screen. The bright bands correspond to constructive interference of light and dark bands correspond to destructive interference of light. Let's now study the interference pattern in detail. Let the distance between S1 and S2 be d, and the distance between the pinholes and the screen be d. Let AB be the perpendicular bisector of the line joining S1 and S2, and O be the point of intersection of the line and the screen. We shall now consider an arbitrary point P on the screen along a line GG' perpendicular to AB and passing through O. Let the distance OP be x. Light from the two sources S1 and S2 covers a distance of S1p and S2P respectively to reach the point P. If P corresponds to an interference maxima, then the path difference S2P minus S1P is equal to n lambda. Let this be equation 1. On the other hand, if P corresponds to an interference minima, the path difference S2P minus S1P is be equal to n plus half into lambda. Let this be equation 2. Here, lambda is the wavelength of the light waves and n is an integer. From the diagram, as shown, we can write that S2P square is equal to d square plus x plus d by 2 whole square. This is equal to d square plus x square plus d square by 4 plus xd. Similarly, S1P square is equal to d square plus x minus d by 2 whole square. This is equal to d square plus x square plus d square by 4 minus xd. Therefore, S2P square minus S1P square is equal to 2xd. This equation can also be written as S2P minus S1P is equal to 2xd by S2P plus S1P. If capital D is much greater than the small d, then we can assume that S2P plus S1P is approximately equal to 2d. Then the path difference S2P minus S1P is equal to x into d by d. Let this be equation 3. From equations 1 and 3, the condition for point P to correspond to a bright band is x into d by d is equal to n lambda, or x is equal to n lambda d by d. Let this be equation 4. From equations 2 and 3, if x d by d is equal to n plus half into lambda, then at point P we will have a dark fringe. That is, for a dark fringe, x is equal to n plus half into lambda into d by d. Let this be equation 5. Here, n is equal to 0, or plus or minus 1, or plus or minus 2, and so on. The distance between the centers of consecutive bright fringes or consecutive dark fringes is called the fringe width. If xn and xn plus 1 are the distances of the nth and n plus 1th bright or dark fringes from the central bright fringe, then mathematically fringe width is equal to xn plus 1 minus xn. From equation 4, the fringe width for a bright fringe can be written as lambda d by d. From equation 5, the fringe width for a dark fringe can also be written as lambda d by d. Hence, the fringe width is the same for both the dark and bright fringes, which means the dark and bright fringes are equally spaced. If the fringe width is represented by beta, then beta is equal to lambda d by d. Let this be equation 6.